Good afternoon, biology. Today we are going to begin our discussion of Chapter 9. Chapter 9 is on respiration. Most of you probably associate the word respiration with breathing, right? Breathing in and breathing out. You're not far off from what we're talking about. We're talking about at the cellular level what happens with our respiration. And of course, as we breathe in, we're taking in oxygen, right? And as we breathe out, we're breathing out CO2. So we're going to see what that means in terms of cells and also how that relates to Chapter 8, photosynthesis. Okay. All right. So Chapter 9, cell respiration. Here's the definition. The definition is the process that allows living things to obtain energy from their food. Oxygen is used. And that might sound a lot different from what we just mentioned with breathing, right? But notice oxygen is used. Okay. And so really when we think about it, when you're taking in air and breathing, getting your oxygen, what's that oxygen used for? Okay. Getting our energy. All right. And so we're going to see how that works. The main organelle to do this is mitochondria, the powerhouse of the cell, right? So now we're going to see what does that mean. Okay. We're going to see how it is the powerhouse. How does it generate energy for us? How does it help to do that? All right, here's the formula. And just like the photosynthesis one, you do need to know this. And if you look at it, though, it might look very familiar. Okay. Here it is in words. We've got oxygen and glucose as reactants. So O2 and C6H12O6. And our products this time are carbon dioxide, water, and we get an energy component. Okay, so if you look at that, CO2 is carbon dioxide, H2O is water. Maybe now it looks a little more familiar. Okay, think about what we do as humans. Okay, we breathe, we eat, we breathe out, we breathe out and perspirate and get rid of water in other ways, right? And we can move around. So if we look here at the picture, I know I have my stop sharing thing in the way. I don't want to do anything there. I might lose it. But this little yellow starburst says energy down there. Okay. So here it says cellular respiration, shows two probably middle school age kids, and they like to eat, right? It says glucose/food. Even if we eat meat, all food chains begin with a green plant, which has glucose. And we did that in the review the other day. I had you trace back your food, and it ultimately got to a plant, didn't it? So whether you like to eat, look at this meal, peppers, grapes, tomatoes, strawberries, and cake, pick your favorite, you eat that, right? It has glucose. You breathe in oxygen. Water, we breathe out water vapor, right? Breathe on a mirror or a cold window in your car, it fogs up, right? We breathe out water vapor. We also lose water through perspiration. You're sweating. We breathe out CO2, and we can receive energy from our food and make us jump around like a tiger, apparently. All right. Now we go to this slide and we look and notice what we've got here, guys. Photosynthesis. I am going to hide this now because it's covering up what I need. Let's see if I can do it. All right. Okay. So photosynthesis and cell respiration are connected. All right. And so what it becomes is sugar, the big one here, okay, that's a product of photosynthesis. Plants make glucose, and then things like rabbits, heterotrophs, they eat it, right? Plants make oxygen. Rabbits breathe it. The rabbit sweats or breathes out water vapor. That water can make its way back into a plant through the water cycle. The rabbit breathes out CO2. The plant takes in CO2. And so you can see the reactants of one chemical equation are the products of the other one. And the products of the one chemical equation are the reactants of the other. Okay. And so once you learn one of these, you automatically just flip them. That's the other one. Okay. So this stuff's a lot simpler than maybe initially you thought. Also, take note that heterotrophs are going to give off some energy. They move around, right? ATP is going to help this rabbit to hop and chew and escape and mate and things like that. The rabbit also gives off heat energy. Okay. As do all living things. So if you cuddle up next to a rabbit, it feels nice and warm and cozy because he's giving off heat, right? All right, we're going to talk about calories next. And this is how we express the amount of energy that is stored in some of these glucose items, like cake or strawberries or grapes. It's expressed as a calorie. And in order to use the energy that is contained in those molecules, we got to break the bonds. Okay, we got to break down that glucose. All right. And so you guys are probably familiar with the calorie. Now, one little tidbit here. The calories you see on nutrition labels technically are different than the lowercase calorie in physics. Okay. It all deals with how much water can be heated 1 degree Celsius, the energy required to do that. The calories in food are actually 1,000 of those other calories. So it's like a kilocalorie. But since most people are familiar with nutrition labels and in life, that's going to mean a lot more to you unless you're some physics professor or some physicist. We'll just, from here on out, think of it as nutrition calories. Okay. But this is pretty interesting. The calories in these items. So if you could take the energy levels of the food that is stored in this food, okay, the energy stored here in 5 pounds of spaghetti, which would be about 5 standard boxes of spaghetti that you have in your cupboard. That'd be enough energy in there to brew a pot of coffee. Kind of interesting. 1 piece of cherry cheesecake. This is I think back to my Thanksgiving, and I had more than 1 piece of cheesecake. I'll tell you that. 1 piece of cheesecake can power a 60-watt light bulb, like a standard light bulb in your house, for an hour and a half. So, if you say, I got to exercise to wear off that cheesecake, you're right. Okay. This one might be questionable. I cannot tell if there's a decimal there or not. I think there isn't. Okay. I think that's 217 Big Macs is enough energy in there to power a car for 88 miles, which is pretty surprising. Big Macs are pretty high calorie. So I had a friend in high school that ate 10 Big Macs at once. Pretty amazing to see. That's a lot of calories. Probably enough for a week. Okay, so how many calories do you need in a day? You guys might know. Here it is. Okay, so this is kind of a average table. I guess you could probably find different values depending on the source, but this one is pretty standard, I think. If your previous answer in your head was 2,000, that's about average. Okay, about 2,000 calories a day. Notice it depends on age. Okay, for the most part, a person that's in their teens or their adult years are larger than a child, so they're going to need more, right? Bigger the creature, the more it needs, right? We talked about lab cell size in a lab earlier this year. Also, interestingly, males require a little more calories than a female. Some of that is due to composition differences. Males tend to be more muscular and less fat content than females. So that affects the necessary calorie requirement to function. So males tend to eat a little more, maybe by choice too, right? Although I've seen teenagers, doesn't matter what gender they are, can really eat and put down food. Now, Also, your activity level depends. So sedentary means, it doesn't really do much. Okay. Active would be like, you're like one of the maybe you're a high school athlete and you're getting up in the morning and you're going to practice, or you're getting up and you're doing your schoolwork, and then you're moving around all day, and then you got practice, and then you're doing other stuff for fun. That would be active. I would guess most people fall into the moderately active situation. But either way, find your gender, whether you're male or female. Find your age. I would guess you guys fall into the 14 to 18, and look at your calorie intake. And you might be surprised how many is there, and maybe what you actually get. So maybe at our next meeting in person, we can discuss this and see how many of you actually do look at your calories. I think you guys are at the age now where your metabolisms are high, and you should enjoy the fact that you can eat pretty much whatever you want and not have to worry about it. But if you're in a sport or something, we find sometimes that kids don't take in enough, and they aren't eating enough calories, and that can keep you from getting to your potential. So, if you've ever paid attention to that, cool. If you haven't, maybe keep track of it one day and see where you're at. Now, if you're really active, let's say you're Michael Phelps, arguably the greatest swimmer of all time. I don't know how many gold medals he won offhand, but it's a lot, right? He was pretty much untouchable, in many of his races. So to get to that level, not only do you need some natural talent, but you also have to train a lot. And look at what he would do during a training, like a training day. All right. So breakfast, you guys, we said 2,000 calories is enough. Well, he doubles that just for breakfast. So we got 3 fried egg sandwiches with cheese, lettuce, and tomatoes, an omelet, grits, French toast, pancakes, 2 cups of coffee. Okay. Lunch, 4,000 calories, a pound of pasta, you guys, a whole box of pasta, 2 huge ham and egg and mayo sandwiches, and energy drinks. And then dinner, another 4,000 calories, another pound of pasta, almost an entire pizza. I think most pizzas are like 8 slices, and energy drinks. Okay. Is this accurate? We're taking the Baltimore Sun's word for it. But you also have to remember, taking in that many calories in a day, he's doing it because he's burning that many calories in a day. And so you also have to think about the type of workouts he's going through. And so Michael Phelps, when he's practicing, several hours a day, plus he's eating these meals, there's not much time for much else, is there? Sleep, eat, and train. Pretty crazy to see how much is needed. You drive a car fast enough and enough, you need more fuel, right? That's pretty much what it comes down to. All right, we are going to cover in our next video the 3 stages of cellular respiration. And unlike photosynthesis, we're going to break it down into the steps. Okay, we're going to talk about glycolysis, Krebs cycle, and electron transport. And those might not mean much to you at this moment, and that's fine. Okay. But just as an intro, okay, I'll give you this. So we see glycolysis up here. And we're going to look at these things fairly simply. If you've looked through the notes already, you probably saw a lot of detail. We will overlook some of that detail. So glycolysis, we're going to focus on glucose going from this stage to this stage. So if that looks to you like it's breaking down into 2 things, you are correct. Okay. And we're going to look at the ATP generated. All right. Krebs cycle, it's called a cycle because of a repetitive aspect. Okay. We're going to get some ATP out of that. And electron transport. Okay. Something going in, something coming out, and we're getting ATP from that as well. Okay. So just for right now, a question I would expect you to be able to answer is, which of these 3 take place in the mitochondria? Okay. And so that's what this is. This orange or terracotta perhaps, colored thing. This is mitochondria. So based on that diagram, the answer would be what? It'd be the Krebs cycle and the electron transport chain. Okay, those happen in the mitochondria, in the powerhouse of the cell. So these are some of the mechanics behind the powerhouse of the cell definition. Glycolysis happens near the mitochondria, but not in the mitochondria. Okay. All right, one last thing here. Aerobic and anaerobic. We're going to mention these words as we discuss these things. Simply, I know most people are used to the word aerobics, and they think of, your grandma going to a class at the YMCA or something. It could be. But the reason they call it an aerobic exercise is, you're working on the aerobic component. Okay, in science, aerobic means with oxygen, anaerobic means without. Okay, so we know out of these 3 cycles, 2 of them deal with oxygen, and so they're called aerobic components. And anaerobic means without, and so glycolysis happens really without oxygen. Okay, what does this mean for us? As we get into this a little further, these are the connections I want to make with you. So as a track coach, I've coached cross country in the past as well. I was involved in both those sports in track and in high school, and I've done some ultra running beyond college. We can look at sports and break them down, and we can kind of categorize some of them as aerobic sports and some as anaerobic, although most sports utilize some of each. But we can usually say one's more heavy in one over the other. So an aerobic activity, like distance running, okay? Here's Anton Kuprichka. He's one of the best ultra runners in the world. In this picture, he's probably running 100 miles. That's very aerobic. Okay. I mean, can you hold your breath for 100 miles? No, right? You can't. You're breathing in oxygen. But sprinting, on the other hand, sprinting is very short. Okay. So this guy maybe is running the 100 meters in, 10 seconds. Okay. You actually do that prior to really requiring much oxygen. Okay. That race is over before it really becomes a necessary thing. And so sprinting, they would consider more anaerobic. Okay. Powerful weightlifting, like doing maxing out on bench press or squats, anaerobic. Okay. Hockey, doing a 45-second shift in hockey, much more anaerobic. Could you hold your breath the whole time? I don't know if it's advisable, but it's such a quick and explosive and fast series of motions. You don't get into the aerobic component. Okay. So, training is geared that way. You don't go run 10 miles for a hockey practice, right? Okay. Does that mean distance runners never sprint? Of course not. Okay. So a lot of science behind it. I almost wish there was a sports science class we could teach as coaches. It'd be awesome. I love reading about this stuff. But here's some aerobic type, cardio and endurance type things, where exercise geared for muscle mass, speed, and strength, plyometrics and things like that, more anaerobic. So the way you can tell is you kind of go by feel. Okay. The anaerobic things tend to hurt more. Lactic acid buildup, sprints. And I know in track, kids, the day of speed workouts, kids fear those. Really not necessary to fear them, but they let it psychs them out. Talk test is a good one. If you can talk comfortably and converse while you're exercising, you're in the aerobic stage. Okay. You're on an elliptical and just kind of going nice and easy and visiting with somebody. That's aerobic. Okay. You're not going to tell someone's life story during a down of football, right? You're too anaerobic. You're trying to be explosive, right? You're not out there during a hockey shift having a conversation with somebody. Okay, you can't, right? It's because it's so anaerobic. So hopefully that makes sense. Okay, Oh, yep, that's where I wanted to stop. So thanks for watching, and I got to figure out how to end my video.